first test going to be on Chapter 11 and 12.6?
Probably just Chapter 11.
Okay.
Yeah, because I want to cover more in 12 than just 12.6.
Okay.
I'll probably try to do it quickly. In fact, I'll take a look and maybe we'll just do 11 and 12 together. That might be the best thing to do. Because we need to move along because we've got some important thing to get to. Okay. All right, we are now recording. Let's get the slideshow set up from the current slide. And slow as this seems, it's much faster than it was this morning. Hide presenter view and come up with the other view. Here we go. All right. For some reason today, it's skewing everything to the right. Of course, it's done this occasionally before, but it was even doing it in my first class when it seldom does it. So I don't know, it just does whatever it wants to, I guess. All right. This won't last for long, but just so you'll see it a little better while we're talking about it. Yeah, see, everything's skewed, and I don't know why. Now, example 4, we were talking about velocities and speeds, and we finished that one, I think, adequately. Then in the middle of the page, 593, there's a paragraph that starts, in physics, we often describe the path of a particle moving with constant speed along a circle of radius capital R in terms of a constant omega, lowercase Greek omega. It looks like a W. That is an omega. Okay? All right. Omega. Now what that is the, in terms of constant omega, that is angular speed. And this formula, no, they don't show it here. Let me write the formula down, which means I've got to, of course, when I go to write, that all shrinks again. Okay. It's following a we're moving along a circle, and the path it's taking is C of t, and that C of t is R cosine omega t, comma, R sine omega t. Now let me say a little bit about this notation. I think we've been playing with it and using it a little bit, but just to get a thing. This is a parametric function describing the path it's taking as a function of time, or t. It doesn't have to be time, but it is. Okay? It's a circular path, so we know it's going to be on a circle. The radius of the circle is r. Okay, any radius there is r. Now, cosine omega t, r sine omega t. Cosine omega t, if you remember, that's your x coordinate. Okay, cosine is your x coordinate, and sine is the y coordinate. So, and by the way, if you squared this and squared that, okay, r squared cosine squared omega t plus r squared sine squared omega t, add them together, you would factor out r squared, okay, and then you would have times 1, okay? Well, that would give you a circle of radius r, okay? So sure enough, that's what we've got here, okay? Now, these look like coordinates. They are. It also looks kind of like a vector, except in our text before, vectors have been angle brackets. This book, I think, uses parentheses there. So, but this isn't indicated as a vector, okay? But it's sort of acting as either a vector or a scalar, as our vector components are are scalar coordinates, and it really is either one, okay? But anyway, there is your function that's describing circular motion centered at the origin of radius r, okay? Now, and angular speed omega. Then omega, which is radians per second, angular speed radians per second, times t in seconds would be radians. Cosine of radian, sine of radians, okay? Those are what you take. Okay. Now, the constant w is called the angular velocity or angular speed. Is the rate of change with respect to time of the particle's angle, not of any displacement of the angle. If this is the angle here, theta, then the time rate of change of that theta would be omega. So therefore, going the other way, theta would be omega t. So that's why that's your cosine of this omega t. That would be your x coordinate here, and your y coordinate would be the sine of that omega t. That would be the y coordinate. So there's your, this is a point. These are coordinates for the point. The x coordinate is r cosine omega t, the y coordinate is r sine omega t. Okay. So let's move to example 5. Angular velocity. Calculate the speed of the circular path of radius r, capital R, angular velocity omega. Calculate the speed of the circular path. Okay, I think that probably should be on the circular path. The paths had speed. I think that should be on the circular path of radius r, angular velocity omega. Okay? So if this is your position, what would be your speed? Time rate of change of position. Would that do it? Physics students? First derivative of position, that's your velocity, speed, right? So let's take a derivative. What would that be? C prime of t, which I contend is going to be omega of t, would then be what? I'm going to do this as if this was a vector, but in fact they do this and it does become a vector. What would that be?
Would it be r sine t? Sine w t?
Yeah, if I could get this to get out of there. Sine. Now it disappears. Omega t is not a w, an omega. Okay.
And then r.
Not quite.
It'd be rt, or would it be rw t?
Yeah, r omega, because t is your variable that you're taking with respect to, but then derivative of cosine is negative sine, okay? And then for the y coordinate, that would be r omega. What did you say? I couldn't hear. Cosine omega t. Okay, very good. Okay, that would be your velocity. And this happens to be a vector, okay? Now let's think. For this one where it is now, here's r cosine omega t, r sine omega t. X coordinate, y coordinate, okay? Now, what we've just done, the velocity, since it's moving in this direction, its velocity is always tangent to the curve, and that would have a negative x coordinate, okay, because it's a little that way from where you are here, and a negative y coordinate because cosine omega in this is your theta here, second quadrant, that would be negative 2. So sure enough, that would have a component negative in x and negative in y. Okay? And here we have Victor. He's been waiting all day to say that. Okay. So, all right. Humor him. Okay. What we just did, this was called our x of t. This was called our y of t. And what we just did was come up with the x prime of t, which is what this is, and this is our y prime of t. Okay, so those are, indeed, that's your, okay. Now, that would be velocities. What it really asked for was speed. How do we define speed?
That's a scalar.
Yes, a scalar.
And it's not a vector.
Not a vector. Victor. Okay. And, I can't read. Here we have, is it Tony?
Yes, sir.
Okay, I thought so. All right. Half of our attendees are here now. We've got 3 other people who haven't attended, but.
So we need to find the scalar of that.
Okay. Well, let's go back to vector. Velocity being a vector, what is speed? It is a scalar, but how does it relate to velocity?
As a function of time.
Okay, yeah, it would be a function of time. If this is my velocity, that would be the x coordinate and the y coordinate. What would be my speed? The length of that. You're absolutely right. And how do we get the length of the hypotenuse? We use the Pythagorean theorem. So the speed is a function of time. And let's see, I think they called it here. They don't call it anything. Let's call it v without the vector over it, v of t. And that would be, how does Pythagorean theorem go? The square root of x prime squared, which would be r squared, omega squared, sine squared omega t, plus y prime squared, which would be r squared, omega squared, cosine squared omega t. And what can we pull out of that?
Well, we can pull out a r squared omega squared.
The square root of that, which would be r omega. And what's left? Of? Yes, the square root of sine squared plus cosine squared, which is 1. So here's what our speed would be, r omega. Okay? Now, they put this in absolute values. Yeah, I guess you have to, because omega could be a negative value, but speed is always a positive value. And r is always a positive value. Yeah, if you were going the other way, that would be a negative omega. So it's the absolute value of that omega. We usually think of it as r omega. Okay. But technically it is that. Okay. Now, by the way, the displacement is, and why they change variables like this, I don't know. Rather than write, I'm not blinded by the light here. Jonathan? Second. Oh, Nigel. Sorry, I'll use that. Okay. All right. 5 out of the 8 attenders are here. Good to see. Getting back up almost to our average now. Okay. Now, here the curve is called C of t, but the distance traveled on the curve is typically called s of t. Okay? That doesn't stand for speed, that's a distance. And then the velocity would be s prime of t, which is exactly what so this is the magnitude of s prime of t, v of t, s prime of t. I hesitated to introduce the s because you think of it in terms of speed, and it's not. It's a displacement. Okay. Now, the second part of this question says, what is the speed if r is equal to 3 and omega is equal to 4, and that's 3 meters, and omega is equal to 4 radians per second. Okay. Radian really isn't a measure of anything. It's not really a unit, but the book calls it rads per second. So what would be then its speed, which we just found here? Is what? 12 meters per second. Because you really realize radians aren't really a unit of anything. That's a ratio. So it's not really a unit. They put it there. When you multiply that together, that's not really a unit. It's just meters per second.
They probably just put there's placeholders 8 per second.
Yeah.
Not per minute or hour.
Yeah. Well, or you could put second to the minus 1. But then you think of that as being a frequency, and that's not far off from being a frequency, except a frequency isn't an angle per second, it's just cycles per second, which is not a unit either. So they... Yeah, you can think of it that way. I'm trying to think if you could call the radius meters per radian, and I think you probably could, because along a circle, 1 radian is 1 radius is moved in 1 radian. Well, 1 radian is about 58 something other degrees. That's when you move 1 radius. So you could call this the radius is 3 meters per radian, and when you multiply that, the radians cancel out. You could say that. Let's not. Okay, but you could. Okay. Now, this is a math book. They really don't worry about units that much, so sorry about that. Now, consider the surface obtained by rotating. This is a new subject here. They don't do anything to tell you. Consider the surface obtained by rotating a parametric curve, and the only thing that's similar is this curve is c is equal to x of t, y of t. Okay? Doesn't have to be a circle, but some curve, x of t, y of t, about the x-axis, say. Okay? Now, if we did this around the x-axis, this curve here, then I would say let's only use half the curve, because you're going to rotate it around the x-axis. What have you formed? A sphere. This is a circle. When you rotate it, it would be a sphere, a ball. Okay? So that's the type of thing they're talking about, but you don't have to have this curve. It could be any old curve rotating around the x-axis. Okay? Consider the surface obtained when you do that. The surface area is given by equation 4 in the next theorem, so let's go on and get it up here. Okay? Now, we'll talk about what it is and then maybe infer things to help remember it. I don't know why it's cutting off the end there. And by the way, for those who haven't been here before, Cameron was here yesterday, they came in last Thursday after our classes and resurfaced these whiteboards and also resurfaced the blackboard with the whiteboard. So now this is Jonathan, right? Okay. We're missing Matt. He's usually here. And one more. Oh, Ashley has been here, but she hasn't last week or this week yet. Okay. So what we're doing, rotating the curve, C of t, which is defined by some parametric equations, x of t, y of t, x of t, y of t, where y of t is always greater than or equal to 0, and x of t is increasing, and x prime of t and y prime of t are continuous. Okay? Then the surface obtained by rotating that curve, C of t, around the x-axis between t is equal to a and t is equal to b has this surface area. Okay? Well, let's look at it. Capital S surface area, little s was displacement. Capital S surface area, 2 pi times the integral y of t times, does that look familiar? What was that? Right. And that basically was the speed, wasn't it? Remember? Okay. Now, I frankly don't like putting the squares here. The book does. I like to put the squares back here right past the primes. Superscripted right past the primes. Because you don't think of doing t squared. It's not t squared. It's the function, derivative of that function squared. Okay? Now, let's see if that sort of makes sense. This, remember, was sort of like our speed, but when you multiply speed by dt, you get an increment, okay? And then multiply that by y of t. Well, why the y of t? Let's sort of draw us a little picture here, okay? Now, of course, when I go to draw the picture, that shrinks. So, I think we're okay. All right. Here's the, how do you want the surface to be? Something like that. It could be a loop-de-loop. Well, no, it couldn't. What's required is y to be greater than 0, so I did that, greater than or equal to 0. X increasing, so I can't have x backing up. Okay, so this is a fair rendition. Okay, and let this be your A, this be to B. Okay, in that interval, these things have to be true. Okay, all the x prime and y prime are continuous. So the surface obtained by rotating that about the x-axis. Okay, well, you're rotating this around the x-axis, so basically you get something down here that looks like that. I don't know if I got it done well. So this is going around. I probably didn't make it quite far enough down. You have circles at the ends there. Now, the only reason I drew the circles there is trying to illustrate for you what the surface area is basically going to be a little increment here, right? Rotated about this radius here. So it's going to be like that, right? A little piece of the cylinder, right? It's going to be rotated. Well, remember now, this is the x-axis, this is the y-axis, okay? Now, the length of this thing here, this little chunk of cylinder there, is dx. But what in the world is your dx here, okay? That would be your ds. Remember, your little s is your increment here. That little increment, maybe I should do a different color. What color would you like that? Blue? Okay. I'm going to go with light. It might show up better. Okay. This little increment here, that's your s. Okay? And that little increment s is what gets revolved around the x-axis. Okay? Now, that little increment. Remember this part, though. Let's go back to black. Okay? This part right here is, remember, this is your ds. dt is equal to the integral. Yeah. No, I'm sorry. Not the integral, the square root. Okay. Okay. This is your square root of x prime squared of t plus y prime squared of t. Okay? That's what your incremental ds is. Okay, from above. That's what we did before. Okay? So therefore, your ds is equal to x prime squared of t plus y prime squared of t dt. Isn't it? Written as a derivative, right, as a differential, and that's what, so this thing right here is your ds. That's what I said originally, but I thought that's not describing it too well. That's your ds, and that little ds, that little increment of this, has to go around what? The what? The x-axis. Okay, around the x-axis. What distance does that travel?
The y of t.
The what?
Y of t.
A little more than that. What is your y of t here? This is a one-dimensional thing. This is coming out, going in that distance. So that basically is your radius here, right? And how far does that travel going around? It's a little circle, right? Forms a circle. What?
360 degrees.
Okay. Which is how many radians? 2 pi. Okay. 2 pi y is the circumference of that circle we've got there. That slice that we have here, the circumference of that is 2 pi y. Here the y is a little shorter, here the y is a little longer, but any segment here is its radius is your y of t. So 2 pi times the y of t is the circumference times the width of that, which is your x of t dt. Sum all those up, you got it. Okay? That's your surface area. Okay? I don't know if that makes it any easier to remember, but that's what you got. You got a circumference of 2 pi, circumference of y of t. So 2 pi times that radius, that circumference is 2 pi y of t, where your y of t is the radius, so 2 pi r is your circumference, times your incremental ds, and that incremental ds is your speed times your time. That gives you your displacement. Okay? I don't know if that's helpful, but I don't like memorizing formulas, so I like to think through what they mean. So let's do example 6. Okay, I think this has a picture. Here it is, a megaphone, or something like that. Boy, this one looks a little different from the one in the text. Okay? Yeah, very different from the one in the text. Let's see how different this is. Calculate the surface area of the surface obtained by rotating the parametric curve C of t is equal to t cubed. Oh, please, yeah. I don't care about a tractress and hyperbolic secants and tangents. Yeah, forget that one. Let's do the one that's in the book. This is the better example 6. Except now I have to draw it. So what I think I'll do is go to a white screen, try to draw it there. Okay, here is my y-axis, my x-axis, y, x, okay. and I'm drawing from 0 to something,
Yes.
and we're doing the curve. C of t is t cubed. C of t is equal to t cubed. Okay? Now, give me a t. Keep it 0. What is your x and y component? 0, 0. Got it. Give me another t. 1. Okay? Let's do, I'm going to try to do it like, let's see what, no, they're going 0 to 1. So we'll do this is 1, that is 1, and that is 1. Okay? So, what's your x component?
1.
And what's your y component? 1. So we're up here. Okay, we might need to do something a little closer in, so let's do a half, or 0.5, whichever you want to call it. What would be your x of t? 1/2. And your y of t would then be? 1 what? 1/8. That would be a half, that would be a quarter, that would be a eighth. So there would be that point. So that's why it's going like this. Sort of ugly drawing here, but there's your megaphone. Okay, there's your megaphone. All right, to get the surface area of that, t from 0 to 1, and that's a sort of poor rendition, but something kind of like what it's looking like. Okay, so what is our surface area? Formula we just had? Say again? 2 pi times the integral from 0 to 1. The t's are going from 0 to 1. Say again? Y of t, what's your y of t? T cubed. Okay. The square root of? Okay, what's x prime? 1. 1 squared is? 1 plus? What's your y prime? Second, 3 t squared, that's y prime. Square that and you get 9 t to the 4th, and then you get a dt. Right? Okay, I believe that'll do it. How are we going to do that integral? What would you suggest? Second? How are we going to do that? Lazy bones, okay.
It's too high power to be a trig function.
Right.
1 plus something that's nice.
Uh-huh.
You could do substitution maybe?
Yes, let's try substitution. Let, what you want to call it? U, why not? Okay. Equal 1 plus 9 t to the 4th. Okay, let's see what that'll do. Then du is equal to 36 t cubed dt. All right. Well, we don't want 36 t cubed dt. We want t cubed dt. See there's your t cubed dt right there. So let's divide both sides by 36. So when we change our variable by substitution, you'll have s now as a function of u rather than t, but it's going to be definite, so we don't have to do that. 2 pi over 36, which by the way is pi over 18. Okay, I'll just pull that over 36 out. Our integral then, we'll do the limits in a minute. And what do we have here? Which I'm going to call u to the 1/2 du. Does everybody see what we did there? Okay, now let's deal with the limits. When t is equal to 0, see t equals 0 here, what's u equal to? 1. And when t is equal to 1, what is u equal to? Second? I don't think so. 10. Okay. 1 cubed, 1 to the 4th power is 1, times 9 is 9, plus 1 is 10. Okay. So what do we have? Your surface area is equal to pi 18ths. Ugly writing. And what's the antiderivative of u to the 1/2? Help me. U to the, okay, wait, u to the 3/2. So what would be your multiplier? 2/3. 2/3 u to the 3/2 evaluated from 1 to 10. Okay? Boo hiss, okay? This will be pi 18ths. And in fact, let's pull out some more. That 2/3 is going to be in there throughout. So let's pull that out too and make it 2/3 out here. 2 will go into 18 9 times. So this will be pi, well, I'll leave the pi there, 27th. Okay. This because it's just getting a little messy. It's been a little messy, hasn't it? Wait, that's it. Pen. Okay. So this will be 27 down here. Pi 27ths times, we pulled out the 2/3 now. That would be the square root of 10 cubed. Okay. The square root of 10 cubed minus 1, because the square root of 1 is 1, okay, and 1 cubed is 1. So if you got a calculator, do the square root of 10, cube that, or raise 10 to the 3/2 power, I don't care how you do it, subtract 1 from that. That's going to be a little more than 3. Subtracting 1, it'll be a little more than 2. Multiply that by pi over 27th, which is pretty close to 1/3. No, 1/9. So when you do all that, you should get it's a little bit more than 3 cubed, so that's going to be something more than 27 minus 1, so something more than 26 divided by 20. It's just going to be a little more than pi. Yeah. And sure enough, that's what it is. What do you get? Okay. Those black boxes slow you down, don't they? Anyone get an answer yet? 3.56. 3.1? That's what the book had, okay? And that, they didn't give any units here, so we don't know what that would be in. It would be square something. Square centimeters, square furlongs, square something. I don't know. Okay. All right. Do you see how that works? Okay. Keep up with what you're doing and how to get. Okay. That finishes 11.2. Okay. Some preliminary questions here. What is the definition of arc length? Just generically, it's not a very crucial thing, but just to make sure you know what they're talking about when they're saying. What do we mean by arc length? Okay, the length of an arc. All right, pretty cleverly said. Actually, they mean a math definition now that I look in the back. I was going to say the actual distance along the curve you travel. That to me is arc length. They want an actual definition, which would be, well, not definition, a math description. So I'm going to have to unwhite my screen and white my screen, or get me a white screen. And that would be your arc length, this is little s now, is equal to the integral of square root of x prime squared plus y prime squared of t dt. Okay? And again, that's what we're doing, our little incremental, and then you integrate over the whole thing. That's what they're looking for, I think. When I glance back at it, that would be what they were asking. Yeah, wrong place. Okay. S is equal to, now here in the back of the book they did a capital S. Capital S is surface area. This is not a surface area. This is an arc length. That's little s. So I wish they had done that. And they say from A to B. Okay? Wherever you're going along the curve, T equal A to T equal B. Okay. Can the distance, this is question 2, traveled by a particle ever be less than its displacement? Ever be less than its displacement? Say that again.
It can't be less than, but it can be equal.
It can be equal, yes. When is it equal? If you're traveling along a straight line, then your displacement is equal to your distance traveled. Perfect. Okay. I don't even know if they have that in the back. It's pretty. I could get to the right part of the back. No, they're never less than. They are equal when the curve traced by C of t is a line segment from the initial to final point, and C of t is a one-to-one function. So I guess you had to say all that, but they did. All right, number 3. What is the interpretation of the square root of x prime squared of t plus y prime squared of t? I just hate saying of t squared. Okay. For a particle traveling the trajectory x of t, y of t. What is the interpretation of that? Of that square root itself. The speed, you're absolutely right. That is the speed. The speed at time t. That is what that means. Number 4. A particle travels along a path from 0, 0 to 3, 4. What is the displacement? From 0, 0 to 3, 4. 0, 0 is here. 3, 4 would be up here. What is its displacement? That would be the slope. 4 over 3 would be the slope. What would be its displacement? From here to there, as the crow flies. Five. Okay, this would be 5. 3 squared plus 4 squared equal 25. Square root of that is, okay, 5. Can the distance traveled be determined from the information given? No, this would be the minimum distance traveled, but from the information given, we don't know if it went this way, or if it went that way, or how it went, you know. that way. I mean, it could have gone any way. No, we cannot tell the difference, the distance from the information given. Displacement is 5, and no, we can't tell the difference. Okay, number 5. A particle traverses the parabola y is equal to x squared with constant speed 3 centimeters per second. What is the distance traveled during the first minute? Hint, only simple computation is necessary. A particle traverses... Yes, okay. 3 centimeters per second. 1 minute would be 60 seconds. The distance traveled would be 3 times 60, 180 centimeters. Okay?
I was trying to plug it in for the experts. I'm like, no, I don't think I need it.
It didn't matter what path it's taking. If it's going at a speed of 3 meters per second for 60 seconds, that's how far it traveled. Happens to be along a parabola, so there you can figure out how far along that parabola you got to travel 180 of those units, whatever they were, centimeters, okay? So, but they didn't ask for that. They just said, how far would it travel? Number 6, and by the way, let's just make sure that's all they were looking for. Yep, 180 centimeters, okay? Number 6, if the straight line segment given by C of t is equal to 3 comma t, for t less than or equal to 2, between 0 to 2, if that straight line segment is rotated about the x-axis, what surface area results? And again, hint, only a simple computation is necessary. Oh, wait. Have they said that right? I'm going to have to draw this. Yeah, but all right, using the same scale we did. So convenient. Okay. If the straight line segment given by C of t is equal to 3t, so the x is always 3, the t is going from 0 to 2, that's your y value, that would be vertical line right there. I don't think this is what they meant. Okay? I think they either mean the y-axis or they mean that to be T3. Because I think what they mean is, because you rotate that around the x-axis, you don't get any surface area at all, except maybe a circle, you know. If that's what they're looking for, that is...
That'd be, what, 4 pi?
No, yeah, 4 pi. Pi r squared, that would be 4 pi. I don't think that's what they're looking for, but let me see.
It says only simple computation.
I know, but I don't think that's what they meant. Oh, that is exactly what they meant. Yeah, 4 pi. You rotate this around the x-axis, you just form a solid circle. And the circle is pi r squared. The area of that is r is 2. Pi times 2 squared is 4. That's 4 pi. I thought they meant, they were really meaning, if you did this, T3, and rotate this around, then you would just have a drum, and that would be a fairly simple thing about it. But that's not what they were saying. So, tricky. Okay. Homework exercises, any of the odds 1 through 9. Do 11 or 13, or both if you choose. Do any of the odds 15 through 19. Then do any of the odds 21 through 29. Then do any of the odds 31 to 37, and that's all you have to do. If those are really too easy and boring for you, you can try 39 or 41, okay? But you don't have to. All right, let me think. Do we really need polar coordinates for anything right now? Most of the time I don't do this. You probably need them in physics. I think we've already done a little bit of that. How about let's just doing a slideshow on 11.3. Okay. Because I can't think if there's anything specific we're going to need polar coordinates for. If you've had them in physics, you probably already know how to deal with them. So let's end this show. And let me make sure there were no more slides. I don't guess there were. Yeah, I'm at the bottom. So we'll end that and move on to 11.3 and just basically do a slideshow here, if it'll ever come up. So it's trying now. Here we go. PowerPoint has been incredibly slow all day today. But that's faster than it was this morning, so count yourself lucky. I spoke too soon. Is that it? Yeah, that's it. All right, we're still recording, so let's get the slideshow from here. And we sit and watch a black screen for a while. Why it's so incredibly slow, I don't know. And then I have to get off this presenter view, because that's what's recorded on, not what you see, but what I see is what's recorded on Screencast-O-Matic. So I want to get out of that. Okay, now what I see is what you see. Okay, now this is your XY coordinate system. Pretty familiar with it. What's another name for that? XY coordinate system is also the Cartesian, named after who? René Descartes. Okay, he was a great mathematician, but also a pretty powerful philosopher. One of his most famous quotes, I'm pretty sure you've all heard, you may not know it came from him. Anyone know it? I think, therefore I am. In other words, he said existence depends on the ability to think. He says existence. Okay. Now here is the Cartesian coordinate system. X coordinate, Y coordinate, any ordered pair, XY. Okay, that's the rectangular or Cartesian coordinate for that point right there. But if we were trying to describe that in terms of polar coordinate, we describe that as one distance measure. In other words, that is going to be the distance from the origin to that point. We call that R. And then the angular distance from the initial place, which is your positive x-axis, that's your theta. So this point can be described x, y for rectangular coordinates, or r, theta in polar coordinates. Same thing. Okay, same point is that. Now, how are those two related? Well, this forms a nice little right triangle here. R and theta, x and y. So pretty obvious, x is equal to r times the cosine of theta, right? Good old trick. And y is equal to the r times the sine of theta. Okay, so that's how we express the Cartesian in terms of the polar. How do we form the polar in terms of Cartesian? Well, that's not too bad. that either. This is x, that's y. X squared plus y squared is r squared, right? So what they didn't show here, and of course when I go to write, it's going to shrink the screen, but we understand that. And let's see, I probably need to get my pen activated. So the other way, here they gave the x and y. R is equal to the square root of x squared plus y squared. Now how do we define that theta in terms of x and y? You tell me. What's the relation between theta, y, and x? Second? Inverse is tangent. Tangent of y over x is equal to... Oh wait, no, you're right. Tangent of theta is y over x. So theta is equal to inverse tangent of y over x. So here's a function of x. R is a function of x and y. Theta is a function of x and y. X is a function of r and theta. Y is a function of r and theta. Okay? So generally, when we're doing polar coordinates, we actually use not an xy graph, but we use polar. And what you have then is you would have concentric circles, x equal 1, x equal 2, x equal 4, x equal 8, whatever radii you choose to do that, and then your various angles here, you probably have rays going out at our familiar ones, pi 6, pi thirds, pi halves, 2/3 pi, 5/6 pi, pi half, yeah. And you just go all the way around. I didn't do that right. Pi 6, pi fourths, pi thirds, pi halves. Those are usually the ones we do. Those are common angles that we like to play with most of the time. And then have a variety of concentric circles. Say 0, 2, 4, 6, 8, or whatever. Okay. Then, if you were on the 4 circle, r is equal to 4, and you're at this position where theta is equal to 2/3, that point would be 4 comma 2/3 pi. Okay. Needed to translate that to x and y axis, you just plug in 4 2/3 pi here, calculate that, 4 2/3 pi here, calculate that, and you've got the xy coordinates over here somewhere. Done. Any questions on that? It's just generically how we do these. Now the table that shows what I just, I'm sorry, boy, they don't have these in the right order. This, like I said, was how a polar scale would look if you were actually doing polar coordinates, plotting these things. You usually would have. And by the way, since we moved to the next section, we got things centered again. They're not skewed to the right. What goes on in the mind of this, I don't know. So this would be theta equals 0, pi halves, pi fourths, pi 6, pi fourths, pi thirds, pi halves, 2/3 pi, 3/4 pi, 5/6 pi, yeah. Do them all the way around. They're not evenly spaced because there's a 1/12 of pi between these two, but 1/6 of the pi between those. Yeah. But those are the angles we like to deal with. Okay? And various radii, circle of radius 1, 2, 3. So this point here would be, r would be 3, and theta would be 5/6 pi. 1, 2, 3, 4, 5, 6 pi. Okay. Now, I don't intend this to be something confusing, but I just want to point something out. If that were in rectangular coordinates, it would have one and only one set of coordinates. Okay? But of course, there's an infinite number of thetas that wind up at the same place. Okay? As in, this is 5/6 pi. If you went this way, this would be a minus 7/6 pi. If you went around like that, that would be 17/6 pi. Yeah, you can have, and then, if that wasn't bad enough, this is something a little bizarre in this, if you had a -3 was your radii, then this could be a -pi6 or 11/6. So, because a negative would then throw it this way. You get this angle and then go in the opposite direction. So forget that unless you need it. Only if you have to have that, you need to fiddle around with that. So anyway, that's how we would display things on a polar coordinate grid. All right, now at the bottom of the previous page, here's this. And we've already done this, but I just wanted to say, if you didn't like my writing, here it is. A little bit, not much, but a little bit neater than what I write. Polar to rectangular. If you know the polar coordinate, trying to get rectangular, x is equal to r cosine theta, y is equal to r sine theta. If you know the rectangular and trying to get the polar, r is equal to square root of x squared plus y squared, and tangent theta is equal to y x. That's what I was thinking, but actually when Cameron said inverse tangent, so if you say theta is equal to inverse tangent y over x, which it seems like they call this x, that y, that r. Why not call this theta? Tangent of that. Now, notice there are some restrictions here. This works whatever your r's and thetas are, no problem. This one, like I said, sometimes people refer to minus r's. This definition does not allow a minus r. It's a principal square root. It's always positive. Okay. The other issue here is, of course, x can't be 0 here because, and where is x 0? At pi halves. And of course, tangent's not defined at pi halves. Okay. So you have to understand that's going to be a little bit problematic. And if you do define this in terms of inverse tangent is only defined between negative pi halves and pi halves. So if you're anywhere else, you have to do some manipulation to get it to go there. So this will never produce a negative r, and this will never produce a theta outside of minus pi halves and pi halves. And of course, you've got another half circle over here that you're outside of it. So there are some little problems with that. But don't worry about those unless you need to. Okay. Now this, I think, is an illustration just for a problem. I don't think we have to do anything special to it. Let's just see.
Actually, the circle.
Yeah.
The polar thing was the graphic, for example.
Oh, it was. That was for example. Yeah, I realized that because they had that one point on it, and I knew that was the answer to it. But I just thought I'd use this illustration and say, like this point here. Yeah. The polar coordinates of P satisfy, of course, r is equal to the square root of 3 squared plus 2 squared. That would be 9 plus 4 square root of 13. So r would be square root of 13. And tangent theta is equal to 2 over 3. Okay? Of course, theta is equal to inverse tangent of 2 over 3. That's perfectly fine there, especially in the first quadrant. That works every time. No ambiguity or anything else. Okay? It's only when you're up here, then this has no meaning, or down here, that has no meaning, because it can't be when theta is pi halves, you can't take the tangent of it, or negative pi halves, or 3 halves pi, or whatever. So you do run into a few problems there. But when you get over in this quadrant or this quadrant, inverse tangent doesn't ever get you there, and then you have to do some adjusting. Okay, you have to add pi halves to whatever you get over into the other quadrant. All right. I shouldn't have, well, I said I shouldn't, but here they're going to do the same thing. And this is what I was mentioning earlier, not realizing they were going to say the same thing about it. The angular coordinate of P, which is 0, 2 in rectangular coordinates, is pi halves of any angle pi halves plus 2 pi n, where n is any integer. Okay? Angular coordinate alone. Okay? Now, your formula will produce that exactly. It'll come close. I mean, r equal 2, that would not be a problem. And you can look at it and tell your theta has got to either be pi halves or 5 halves pi, or add another for it, 9 halves pi, or negative 3 halves pi. I mean, you just have an infinite number where n is any integer. You can put in an infinite number of integers there, and it would work. Okay? So they are not unique in the polar coordinate system. That's the only thing it's telling you. All right, and then I think this is the other thing I was talking about. Again, I didn't recall that they were going to show this slide, but here it is. If this is r theta, if we had a minus r theta, then we would do this theta, but then go in the opposite direction for r. So even though they're listed r theta, most of the time we determine the theta, figure out where we are, and then go to r from there. So this point would be minus r theta, or you could have said that was point r theta plus pi. Okay. Again, two very different coordinates for exactly the same point, and you have an infinite problem. Okay. Another minor problem with polar coordinates. Okay, let's look at the same deal with this one. All right, and without looking at exactly what the books say, let's take a look at it. XY points, this is 1 minus 1, this is minus 1, 1. 1 minus 1, minus 1, 1. Okay? Now, what would be that in either of those points in polar coordinates? Okay? I guess let's do this one first. One thing would be 1. No, sorry, what would be the radius here? You know what I'm saying? 1 would be, this is 1, that's 1, that would be beyond 1. This is 1, that's 1. So you cut the arc here, and yeah, it's longer than 1. What's our formula? R is equal to, second? No, that's x is equal to r cosine theta.
X squared plus y squared.
Yes, and that would be minus 1 squared plus 1 squared. Minus 1 squared is 1. 1 squared is 1. 2. So that would be the square root of 2. Square root of.
Yes,
yeah. So that would be the square root of 2. Okay? So it would be square root of 2, 3/4 pi. Okay? Or negative square root of 2 minus 1/4 pi. Okay? Minus 1/4 pi negative square root of 2. Okay? This one down here could be square root of 2, 7/4 pi, or square root of 2, negative pi fourths, or negative square root of 2, 3/4 pi. Yeah! Okay. And you could go around this way and make it whatever that turns out to be, negative 5/4 pi. So that's sort of a little problem with polar coordinates. They don't have unique values. X, Y, they're unique. Any point has only one set. All right, let's see what this one's, if it's saying anything to us that we... Not planning to. I'm just introducing you to it, so if you ever need it, in physics or anywhere else, in engineering, whatever you're doing, if you need it, you've been exposed to it, hopefully you got infected by a little bit of it. Okay. All right. This is just giving some lines, okay? Here's a line through the origin. How would we define that line? Who cares what R is? Theta is equal to theta naught. All here, that's for negative R's, and all up here for positive R's. Any R you want to put there is on that line, okay? So that's how the equation of the line through the origin in polar coordinates would be theta equal theta naught. Whatever that is, that's your equation of the line. Doesn't matter what R is. It can be anywhere from 0 or negative infinity to positive infinity. Okay? Now, here's another line, I think. A line with a slope of 3/2 through the origin. We know if the slope is 3/2, then the tangent of theta must be 3/2. Okay? So then theta naught would be the arctangent of 3/2. So theta equal arctangent. I'm sorry. Yeah, theta equal arctangent of 3/2. That would be the equation for that line. Of course, both of these, all these are going through the origin only. Okay? Make sense? All right. Now, what if it's not going through the origin? Okay. Here's an example of one that's not. Okay. Okay. I don't know how much of this we really need to get into.
Use truth to define where you have the
yeah, I would say this is getting probably beyond what we really need to do, but you could define the line there. And that line is, I don't know what that symbol is. I guess it's this italicized L or something. I don't know what that is. Not a lambda. At first I thought it was a lambda, but I don't believe that's officially a capital lambda. But anyway, you see you got some fiddling around to do on that. R obviously is going from, I'd say let's not mess with that one. Well, maybe we have got it here. Let's see. Whoops. Would this be that equation of that line? R is equal to, yep, that looks like that could be it. D times the secant of theta minus lambda. As you know, secant is never 0. So you could never get a 0 here as long as your D wasn't 0. So yeah, that looks like that would work. Fine. I've never had the need to express a line this, but you could do it, okay, if you needed to. So if we're expressing the tangent line to a circle of radius 4, then obviously in a circle centered at the origin, okay, then the closest point to the origin, that's the thing that we were talking about, that would be your 4, and then the secant of theta minus, in this angle here, they told you that was pi-3 theta minus pi-3. There is an equation of a tangent line. And frankly, that seems a little complicated, but equations of tangent lines are generally not easy to write in rectangular coordinates either. Okay. Now, how about other shapes? Here's a circle. Okay. If that were its origin, that would just be r equal 8. That would be it. Okay. But no, we've got a translation here and other things. And just for right now, word for it, type a word for it. That would be an equation of a circle that happened to go through the origin. Okay. It does touch the origin. And that would be 2a, etc. Without going any more, that actually works for you. Okay. And then they do a little bit on symmetry, and I don't know how important this is. R theta and R minus theta are symmetric with respect to the x-axis. Again, that seems pretty obvious, so I don't think we'll. Okay, I don't know what this one's. It probably has a figure that goes with it. I don't know what it is right now. Okay, this is a line. No. Yeah, it looks like this is a line that goes through. Without belaboring any, if you need it, it's not worth taking too much time on. All right, here's how we go about plotting things using polar coordinate system. Okay, now again, second. Okay, yeah. Let's start with this. Notice they left off the pi quarters here. They're just using the every sixth of a pi. Okay. That makes it a little bit more uniform. You don't have, an extra one in the middle here and there and there and there. That makes it a little strange, but these are usually the easiest one to deal with. Okay, this is here is that thing that we showed. R is equal to 2 cosine theta minus 1. Okay, and what you would typically do is start with theta equals 0. Theta equals 0 is going to be somewhere along the x-axis. And when theta is equal to 0, what's cosine? 1. 2 times 1 is? 2 minus 1 is? So you're starting at 1. Then you increase theta a little bit. And pi 6 is not a bad one to choose. So the theta is pi 6. What's cosine of pi 6? Yeah, the cosine of it would be square root of 3 over 2. 2 times that would be the square root of 3. Minus 1 would be, square root of 3 is 1.7, so it's about 0.7. So that's where you are there. And when theta is equal to 2/3 pi, what is, okay, that's 1/2. 2 times 1/2 is 1, and 1 minus 1 is 0. So when you come in this line, it's at 0. So this is coming in, but never crossing that point. It's at 0, 0, but it isn't just any 0, 0. It's 0, 0 basically with that line there is a tangent to it. Okay? And then it increases, you go to the next one. Okay, now this will get interesting. What if you put in pi halves next? That would be what you would normally put next. That would be -1, and 2 times -1 is -2, minus 1 is -1. So your R, when you're up here at pi halves, you go down here to 1 in the opposite direction. So that's why D shows up next. And, what's that?
Talking about the whole thing. Cosine of pi halves is 0, ain't it?
Oh, you're right. I'm sorry.
I just said -1 overall.
Yeah, -1 is the, okay, yeah. 0 minus 1 is, yeah, right here. Yeah, you're right. Okay, and then when you go over here to 2/3 pi, cosine of 2/3 pi is -1/2 times 2 is
-1.
And -1 minus 1 is
-2.
-2. That's where you go down here.
That's weird.
Yeah, -2. So this is a -1. It goes down here. When you're going in that direction, you go -1. That direction goes -2. This one, 5/6 pi. Cosine of that is. Are we out of time?
Yeah.
Okay. But anyway, that's how you go about plotting. You find your theta first, and then generally calculate the R. Okay. I don't know how far we got in 1-3, but that's all you really need to know. Okay. So we'll start next time at 1-4. This one I think you'll need a little bit more. Okay. So we'll go into this more than just a slideshow. Okay. Good deal. Just seeing you one day this weekend already, I'm telling you, have a good weekend. All right? Seems a shame, doesn't it? Okay. Labor Day did it to us, didn't it? All right. Now, it will be a while before this gets uploaded. Okay? And when it does, though, you'll be able to see it. Sometime later this afternoon, more than likely. When we finish chapter 11, and see that we got 11:4, 11:5 we'll just do a slideshow, and that'll be it. So let's see, what have we covered? Where did we start? Yeah, we started at the very beginning of chapter 11. So we'll do 11:1, 11:2, and 11:4. So it's only 3 sections, probably 3 questions on each of those. One of them will get 4 questions. Probably the area and arc length.
So it won't be a chapter review?
Second?
So it won't be like a chapter review? It won't be a chapter review for the test?
Well, I come in and ask, are there any questions? And that's when we'll do the review. If you have questions anytime, ask them. Okay? So, and you get to take it home too, remember, take-home test. So, and then once you have it home, you can't ask me questions on that, but anything you find in the book, you can ask me questions on. Okay. All right. So we'll do 11:4. This will probably be the section that winds up with 4 questions on it. I haven't made out the test yet, but that's what I'm guessing right now. All right, and we'll see, and we'll have the test sometime after we finish this. I doubt if we'll do this section in a day. Oh, wait. I take that back. Wow. This section is incredibly short. So it's probably going to be one of the other sections I'll have the 4 questions on and try to find 3 in that. Okay. I didn't realize it was that short. Yeah, we probably will finish the section 11:4 next time. So I'll try to have a test ready for you to take home.
1, 2, and 4.
1, 2, and 4. Now, if that's too many questions on too simple of things, I might throw in maybe a very simple question on 11. Which one we just skipped? 3, and maybe something simple on 11:5. If I just need to come up with a couple more questions, but I'll let you know in plenty of time for that. Okay. I think I can get them without that. All right.
I know I'm late. I didn't look at my schedule. I know it started at 12:15. I'm very sorry, but I will be on time.
Okay, well, that's all right, yeah.
I thought it was 12:45. I'd be back in. And my dad looked at me and said today, he said, you sure it starts at 12:45? And when we was coming down the highway, it was just like this. And I looked at it, because I tried to get some rest. I thought it said 12:45. You said 12:15. Because I wanted every time I come in, you already made the lesson. And I'm like, I feel like I'm drunk because I asked him for his notes and everything. I said, okay. But I looked at it and I said, oh my goodness. And then when we got to the exit, it was an accident right there. So I had to go and say, oh man, you got here exactly at 12:45. So from here on out, I'll be here at 12:15.
12:15. Okay, sounds good.